Okay, so how does all this temperature-dependent phenomenon on the hydrophobic effect and just thermal um, um, changes alone impact protein stability? So let's think about that. Um, so what you probably know, hopefully, or what you may remember, is that um, as the temperature increases, proteins unfold in general or denature, right? Okay. So you go back to thinking about the question I sort of started out with in the last section, which was um, the idea that the hydrophobic effect really is the main thing that holds proteins together, main thing that keeps them stable. What we just saw, what we just talked about, is that the strength of the hydrophobic effect increases as the temperature increases, right? So that would seem a little strange. If the main thing that's keeping their protein stable is the hydrophobic effect, then that gets stronger as you increase the temperature. Why would the protein become unstable? It should just get more and more stable, right? That's not what happens, right? So clearly we're missing some things there. Um, the second thing to think about um, is another impact of temperature on protein stability, but at the other end of the scale. Why is it, or why do some proteins denature when it gets cold? All right. This is sometimes known as cold denaturation. All right. Why would that happen? All right. Well, to explain these effects of temperature on protein stability, um, we need to, again, think a little bit more about how temperature is impacting this system of this folded protein polymer in an aqueous environment, which makes us think about or fold in some of the ideas I just presented on the temperature dependence of the hydrophobic effect with the temperature impacts on the other interactions that are important for maintaining a stable protein. All right. So one way to look at this, think about it, is to consider what happens when you do the following type of experiment. If we look at the, as a function of temperature, the amount of heat absorbed by a well-folded protein in solution, right? This sometimes you'll see this presented rather than as the heat absorbed as the differential of the enthalpy, right? So we got a well-folded protein in aqueous solution. We're going to put it into a system, right, into an instrument. And remember, this is also at constant pressure, right? And we're going to increase the temperature. Okay, what happens? Well, as we know for any sort of solution you did this to, the temperature is going to start going up, right? As we start raising the temperature, we're going to see oh, I'm having a hard time with my drawing today. Okay, there's my folded polypeptide. All right, so we're raising the temperature, right? It's going up, right? And we could look at this and say, well, okay, how much heat gets absorbed to get me, say, a 1 degree change in temperature, right? We could integrate under that curve. Right? So we could integrate under that curve. here, and we could answer that question: how much heat was absorbed? Right? That would tell me, right? Okay, but look what happens as the temperature continues to rise. As temperature continues to go up, we get to a point where this system starts to do this. Now look at that, right? At this point, let's say now I want to ask that same question. For a 1 degree rise in temperature, say right in here, say sort of across a similar gap. Let's say this was a 1 degree increase in temperature here. Look at how much heat the system had to absorb in order to get that 1 degree increase in temperature once we get to this point, right? So the question for you now is, why? What's going on there? And of course, if you think about what's happening, we've got a system with a protein well folded in it. As the temperature goes up, we just talked about the fact that the protein's going to unfold. Well, in this region, what's starting to happen is the protein is unfolding, right? The heat put into the system is disrupting those interactions that hold the protein together, and that heat is being absorbed, dissipated into the structure of the polypeptide, disrupting that organized structure rather than heating up the whole solution. So the system's absorbing a lot more heat in order to get a 1 degree temperature rise, because that energy is being dissipated into that organized structure to start breaking it up, right? So this rise is sort of a characteristic curve you see in a heat versus temperature plot for a protein in aqueous solution. Okay, so that's cool, but now consider something else. If you plot this on out and you go on up, at this point, the protein has denatured, you keep looking, you see something very unusual, which is that you get on out here, and I'm exaggerating it, but the plot is going to sort of goes linear again, but it takes off kind of like that. Now, the weird thing here is if you can remember something I told you guys about back at the beginning of the class. Remember, there's this term that relates the heat absorbed or lost, differential heat absorbed or lost, to the differential change in temperature, right? It's called the heat capacity. And if we do this at constant pressure, which we are, the heat capacity, as you recall, is simply equal to dq at constant pressure divided by the temperature. What that means, of course, is that the heat capacity of the folded protein solution, which is down here on the other end, up here where the unfolded polypeptide, the heat capacity of the folded protein solution is just the slope of this line right through here, right? So the slope of that line, right, we'll call that the heat capacity of the native solution, the slope of that line, that's equal to the heat capacity of the native state. By the same token, the slope of this line here that's equal to the heat capacity of the unfolded state, right? Okay. What that means is that if we took a look at the following difference, if we thought about taking the heat capacity of the unfolded state minus the heat capacity of the native state, right? That is not going to be equal to 0. As you notice, the slope has changed, and the slope of the heat capacity in the unfolded state, or that unfolded polypeptide in water, is significantly higher than the heat capacity of the native protein in aqueous solution, right? So that change in heat capacity, right? So-called delta CP, the fact that there is a change in heat capacity and that it's positive, is a striking feature of protein solutions, folded globular protein solutions as a function of temperature. And it's also a common feature of non-polar stuff in aqueous solution. They both share the same sort of feature, which is a change in heat capacity as a function of temperature. Okay, what that means is a couple of things, right? So what is this? Think about this, delta CP, right? That means something. Well, sorry, I guess I should say it's large and positive. And we can write this sort of going from the native to the unfolded state, the change in heat capacity. It's large and positive, right? 2, this may give you a hint of what's going on here. It's proportional to the hydrophobic amino acid content. What that means is if you look at a series of different proteins and you look at the magnitude of that delta CP for different proteins as a function of their hydrophobic amino acid content, the more hydrophobic amino acids they've got, the larger the delta CP. Okay, so you put all of that together, what do you think that means? Why would the unfolded state of a polypeptide in the aqueous solution have a higher heat capacity than the native state? So if you think back to our discussion about what happens to an unfolded polypeptide in aqueous solution, that hydrophobic core that gets exposed to water, what happens? What does the water do? Right? Water forms those clathrates, those organized clathrates around the structure of those exposed hydrophobic amino acids. Right? And in the unfolded state, those high residence time, ice-like water clathrates have these high persistence time hydrogen bonds, right? And those ordered water hydrogen bonding networks can absorb heat, right? And they're going to absorb more heat than the water, the bulk water, that's sort of organized the way bulk water is normally organized around the native state, right? So that delta CP absorption of that heat by that ordered water around the hydrophobic, the exposed hydrophobics, I should say, right, is the reason for this large positive delta CP between the unfolded state, the larger heat capacity, the unfolded state, versus the native state, right? And what that also means, what that also implies, is something we talked about when we did that first transfer equilibrium experiment, and we saw that that enthalpy for that simple transfer experiment was sort of unfavorable, taking the hydrophobic guy out of the water and putting it back in solvent. That actually required some energy, and that phenomenon is related directly to this phenomenon. This large positive delta CP says that there are some favorable interactions between the water and the exposed hydrophobic amino acids in that unfolded polypeptide that require heat to disrupt. And that comes directly from the tendency of water to form these ordered clathrates around those exposed hydrophobics, right? Okay. Now, if you put that phenomenon together with the impacts of temperature on the polypeptide itself, its entropy, we'll come to that in a second, as well as these other interactions that help hold a protein structure together, all of those things together lead to a thermal stability curve for folded globular proteins that looks something like this. So if you think about the free energy, the folding free energy for a polypeptide, all right? So let's say, unfolded to native, right? And so the folding free energy for that equilibrium right here, we're gonna say that's 0. So at that point, right, there is no bias one way or the other, right? And we're gonna think about this as a function of temperature, right? And down here, that delta G for folding is positive, which means down here, the unfolded state is favored. Up here, it's negative. So if the folding free energy is in this upper quadrant, the native state is going to be favored. And what you find for the vast majority of well-folded, well-behaved globular proteins is that these curves look something like this. They're domed. So that almost all proteins have an optimal temperature where they're maximally stable. And as the temperature goes up or down, their stability then decreases, right? So there's this domed spot, right, or maximum as a function of temperature where a protein is optimally stable. So the question then becomes, what's going on down here, right, and down here? So at low temperature, proteins become less stable, and at high temperature, they become less stable. So what's going on? Okay, let's think about that. Let's think about the high temperature case. So at high temperature, what's happening to the protein? All right, you're pumping more heat into the system. You're pumping more heat into the system. What's going on? So over here, when you start doing that, of course, at high temperature, what's happening to the configurational entropy of the protein, right? It's going to go up, right? As the temperature goes up, you're pumping more heat into the system. The configurational entropy of the polypeptide is going to have, it's going to have more and more thermal energy driving that to more and more possible states to populate. So the configurational entropy of the polypeptide is going to go up, right? And what that means, of course, is that the change in configurational entropy to fold the polypeptide at that kind of temperature, right, is going to be larger. If you wanted to try and fold it, it's going to be a bigger and bigger and bigger decrease in the configurational entropy if you wanted to go from the unfolded to the native state. So there's a bigger and bigger and bigger entropic penalty at those higher temperatures to try and fold that polypeptide. At the same time, as you're putting more heat into the system, you're pumping heat into the system, and you're beginning to disrupt all those other stabilizing interactions that would normally hold the protein together. We just saw that in that sort of absorption of heat as a function of temperature. All of that heat that's going into the system is being absorbed and dissipated in all those other interactions that help hold the polypeptide together. So as the temperature goes up, that positive enthalpy change that would normally favor folding, that decreases, right? Now, at the same time, the hydrophobic effect is getting stronger and stronger and stronger as the temperature goes up. But that that sort of increase in the hydrophobic effect, that's going up. It's not nearly big enough to compensate for the drop in stabilizing enthalpy as these other disrupting interactions get blown up by absorbing heat, and the increase in the chain entropy, right? So as the temperature goes up, the protein structure blows apart because the entropy gain of the polypeptide chain itself at those high temperatures, combined with the lack of stabilizing interactions as they get heated up and they get disrupted, the whole organized structure blows up and the protein unfolds. Okay, well, what happens down here at low temperature? How do we explain protein unfolding at low temperature, right? Well, let's think about that. As the temperature goes down, right, the configurational entropy of the protein, the polypeptide chain, that is going to decrease, right? There's less temperature, less movement, right? So the number of isoenergetic states in which that unfolded polypeptide now is going to have an opportunity to populate, that's going to shrink, right? Which means the change in the configurational entropy, right? It's gonna still be less than zero, right? It's still less than zero, but it's gonna get smaller. The delta S change from going from the unfolded state to the native state is not as big a penalty. So the entropic penalty decreases as the temperature goes down between the unfolded polypeptide and the native state. There's less of a loss of entropy, if you want to think about it that way. Okay, what about for the water? What do you think happens to the entropy of the water as the temperature goes down? Its entropy also drops, right? So if the entropy of the bulk water decreases, what do you think happens to the entropy penalty, right? For, say, taking a bulk water, call this like clathrate, right? Making a water clathrate, an ordered water around an exposed hydrophobic. As the temperature goes lower and lower and lower, you're getting closer and closer and closer, if you want to think about it this way, to conditions under which ice would start to become stable. We're not talking about freezing, just getting colder, right? So the entropic penalty of taking bulk water at those lower temperatures and putting it, say, into something that's kind of ice-like gets smaller and smaller and smaller. That entropic penalty is shrinking for putting water into a clathrate. So that's going down. Now, remember, you put water in that sort of ordered, sort of clathrate kind of state around an exposed hydrophobic, you also gain something back, right? Which is you get those stabilizing enthalpic interactions in that ice-like structure that forms. So at low temperature, it's become less, the entropic barrier to folding the peptide goes down, so that gets easier to do. But at the same time, the entropic cost of having the hydrophobics exposed decreases, and the enthalpy, the gain that you would get from forming those hydrogen bonds, actually becomes more favorable. So essentially what happens at these low temperatures in cold denaturation, for some proteins, this doesn't happen to all proteins. It takes a sort of special protein in terms of size and hydrophobic amino acid content. What happens in cold denaturation is that basically the water solubilizes the core of the protein, right? The energetic balance becomes such that it is more energetically favorable for those hydrophobics to be exposed, surrounded by water at that temperature with those high residence time hydrogen bonding networks. And that tips the energetic balance away from the folded state of the polypeptide. There's actually more energy or more more of an energy minimum in having the protein blown apart and the water solubilizing the protein than to have the protein folded up and the water is bulk solvent, right? So that's sort of the sort of energetic explanation as a function of temperature for why a protein's cold in nature. Now for us, for most of the situations that we care about, we're thinking about what's happening right in here at this intermediate temperature, right? Where the delta G of folding is favorable, it's less than 0, right? And for most proteins, it's in this sort of 20 to 50 kilojoule, minus 20 to minus 50 kilojoule per mole range, right? So in this range, of course, what all of this discussion hopefully illustrates for you guys is that the stability of that protein is this trade-off between the stabilizing interactions, right, from the solvent with itself, the solvent with the protein, right, which can support or oppose folding, and the entropy changes for the polypeptide itself, with the need to collapse that unfolded high entropy state to a much lower entropy state versus the change in entropy of the bulk solvent. And depending on the protein, depending on its amino acid content, depending upon the fold that it populates, its hydrophobic content, and the temperature, these different effects kind of slew back and forth between which one dominates and where the protein happens to be stable. So they're compensating for each other in terms of the bulk solvent versus the polypeptide, and governing this sort of dome structure where a polypeptide sits in its sort of barely stable or stable state as this residual sum of these large opposing forces, right? Okay. So just as some final thoughts, right? So in the discussion we just had, right, we sort of come to this conclusion, or hopefully you're with me about the idea that the hydrophobic interaction alone, or the hydrophobic effect, while super important for stabilizing protein structure, the release of the ordered water combined with the van der Waals clustering of the hydrophobic stuff with itself and the enthalpy gain that provides, all of that in terms of reducing the solubility of hydrophobic stuff in solution at temperatures where a protein is stable, right? It definitely, this contributes in a big way. It's important. It's a big contributor to protein stability. Right? But it's not the end all, right? It's not the main thing, all right? There has to be more. And the question is, what else could there be? What else helps stabilize protein structure, right? I've been alluding to it. I've been dropping little hints about it in here, right? What's left? Well, the only thing left, really, is all those weak interactions. Essentially dominated by that enthalpy change for folding, right? That negative enthalpy change, that exothermic tendency to form all of those weak interactions, right? Remember, those salt bridges when they exist. The biggie of those hydrogen bonds, right? That we saw holding alpha helices together and beta sheets and turns, right? All those van der Waals interactions, dipolar interactions between different parts of a protein, between helical dipoles and other surrounding amino acids, the London dispersion and other van der Waals contacts, right? That's what's left. That's all we have left to work with, right? In terms of helping tip the balance the rest of the way into a stable protein. The hydrophobic effect gets us part of the way, but it's not enough, right? What we need to get us all the rest of the way, and just about as important as the hydrophobic effect is all these weak interactions. There's a problem conceptually when you think about that. I'll leave you with this final thought, right? These weak interactions, you know, some you could say, and some people have argued strenuously, that's just not possible. They can't be that big a contributor, because weak interactions are, you know, sort of by definition weak, right? How can they be that important if they're weak, right? Number one. Number two, they're short range, right? How can these weak short range interactions be that an important contributor to global stability of a polypeptide? And the third argument is most of these, less so London dispersion forces on the core of the protein, but all these other guys, salt bridges, you know, hydrogen bonds, other dipolar interactions in van der Waals, these are all screened by water. Right? Hydrogen bond with water versus a hydrogen bond between a backbone amide and carbonyl, it's a hydrogen bond. Hydrogen bonds, hydrogen bonds, hydrogen bond, right? So how could that be a significant contributor? All right. Well, I'm going to leave you with one final observation about well-folded globular proteins, which is something that they do characteristically. If you look at, say, the fraction of the native state, let's say, of a protein, right, in solution, some measurement for nativeness, foldedness of a globular protein solution. And so down here, I'm going to draw this down here again. So this is a little bit different. We're not looking at heat absorbed. We're just looking at how much of the population is in the native state, right? So down here, we'll have like, this will be like 100%. This is kind of backwards, but 100% native, and up here, it's going to be 0%, right? Totally unfolded. And we're going to look at that as a function of temperature again, but instead of measuring heat, we're measuring the population that's in the native state. What you find is that as a function of temperature, the protein will hang out like this, nothing much will happen, and all of a sudden it'll do something like this. Right, and up here we got the unfolded state. So what that curve tells you, and this is, like I said, almost a diagnostic signature of a well-folded globular protein, is that folding of a protein is cooperative. Right? And that cooperative folding or unfolding curve is the answer to this conundrum of how could all these weak interactions be so effectively stabilizing. And we'll talk about that next time.